we'll get started. Okay, first thing I'll do is I updated a bit about the project, so I'll go over that. So I mentioned that for this course, usually for some courses I just let anyone choose any project. Because this is sort of a newer topic, I thought I'd give you a bit of guidance. So I have some suggested pre-approved topics. They're still very general, so there's a lot of different things that you could do within these. And then if you still really want to do something, you have something in mind, that's fine. I just ask that you come and clear it with me first, okay? So if you don't want to talk to me ever and just hand in a PDF when the project is due, make sure it's within one of these topics. I would actually encourage you to look at these topics. I think they're interesting. But if there is something you really want to do, maybe you're doing research anyways on something related to this, that's fine as well. Just come and talk to me about it. Okay? So I split it into sort of three categories. So some of you might want to do something mathematical. Some of you might want to do something just more about reasoning, thinking through use cases, as I call it, or applications. And some of you might want to do some implementation or coding. And so there's a different stream depending on what you want to do. So if you want to do something on the math side or the cryptography side, the protocol that we're covering in this course is called Plonk. Depending on time, I'll try and cover a couple extensions to Plonk, but I'm not sure how far we'll go or how much detail we'll get into them. So what you could do is a deeper dive on some things that make Plonk better, essentially. So there's things that improve its efficiency for provers, called folding. This is the name of one of the systems. These are just two example papers, but there's a lot of other ones on trying to make it more scalable. Can you parallelize different operations? Can you outsource different operations? You probably have heard that there's quantum computing coming. Quantum computing is going to break something that we're about to talk about today, the topic of today's lecture. But Plonk doesn't have to use what I'm going to teach you. I'm going to pick one thing that I think is the easiest to understand. I'm going to teach it to you with the easiest to understand thing, but there's other alternatives to what I'm going to show you that are post-quantum. So there's one called Fry. There's other ones based on lattices, and then there's basically you can combine them with Plonk. So like Plonky2, for example, is an example of a system like that. There's things called lookup arguments. Custom gates are sort of a more generalization of lookup arguments. Way later we'll talk about what those things are. You probably don't have a context for what they are. Custom gates you could sort of understand. You might remember last class we said every circuit you could design with enough addition or multiplication gates only. It might not be the most efficient circuit in the world. So what if you don't want addition or multiplication? What if you want some other operation? That's what a custom gate is. So what you can do is you can define the gate that you want, and then you can use it in your circuit along with addition and multiplication gates. It may make your circuit faster. So there's ways of doing that. Okay, next is more on the use case side. So there's a bunch of scenarios or a bunch of technologies that are very, very close to each other. There isn't a good umbrella term yet for what that is. Otherwise, I would just put it in. But the things are sometimes called ZK-TLS, ZK-email, ZK-PDF. Sometimes they're called web proofs. And they all have a similar flavor. The flavor of it is basically this. Let's say that I get some document from the government. To know that that's an official government document, they will have signed it digitally. Okay, so I have a cryptographic proof that this is from the government. Let's say I get an email. Maybe the email could be from anyone, say an organization, a business. I get an email from Hydro-Quebec. The email server for Hydro-Quebec probably is signing all outbound email addresses. Okay, so whatever that email says, it's kind of like official Hydro-Quebec information. Okay, I could show you that email with the signature and you would believe that my address is what it is or whatever information is inside of that email. Okay, Then if you go to a website, let's say I log in, let's go back to government. So I log into some Quebec government website. Say I go to my tax thing and it has my name and my social insurance number and a bunch of things like that. That's served over a protocol called HTTPS or TLS. And there's some cryptography involved in that. Okay, so there is a key that belongs to the government. And so it's like the content of that website is it's as if it's signed or endorsed by the government. Now with TLS, there's a little bit of a trick that you have to do. There's a bit of a catch where it doesn't work quite as cleanly as the other two because the government isn't directly signing website data. There's a bit more of a protocol that's involved. I'll go through those details for you. Like I said, I'd like to do one use case per class. But before I show you ZK-TLS, I need to show you a bit of cryptography. So we may get it to it this class, and we might have to wait till next class. But I'll give you the sort of how it works in either this class or next class. Okay. So what you can do is this is a very emerging area. Okay. So this is something that people really started talking about just in 2025. So last year. And I don't think people have fully explored all the different things that you could do with it. Okay, so if I'm able to prove things, and the only proof I need is an email that says it, or a website that says it, or a PDF document that says it, right? Then I'm able to create a proof. And when I create the proof, I don't have to repeat all the information, so I can selectively pull pieces out. So what I can do is I can say, I have an email from the government and it says my social insurance number is this. Or I have an email from the government that says my age is this. Or I have a statement from a bank and it says that my bank balance is this. I have a statement from Air Canada and it says I have these many air miles. Okay? And so what I can do is I can create a little proof of that and then I can go show it to people and then maybe I'm able to do something by showing them proofs of it. Okay, so that's what I'd like you to think about, like more like what are the applications of this type of thing. So think about like a novel use case for what you could use this for, and then just explain like who the parties are, what the proof would look like, and that type of stuff. You don't have to give the math of the proof, you just have to give like a specification or a description of what the proof would do and why it would make the world better. Okay. Then for implementation, it's actually related to this. So you could spend more time working on the description of it, or if you want to just jump in with code, you could just try and implement it. So if you were doing the implementation, it could be like a simpler thing, and you're just implementing it to feel out the technology or learn it. Another thing you could do is you could look at the underlying libraries that do this already, that exist, and you could try and find some improvement in one of those libraries. Okay? So to get you started, I mentioned there's a podcast called the ZK Podcast. They have a bunch of episodes on this stuff, but I picked two on the TLS side, one on the PDF side, one on the email side. Again, it's just somebody speaking to someone else, so there's no math, there's nothing that you couldn't say in words, so it should be fairly accessible. And you can listen to it, and they also have lots of ideas about how this stuff could be used. Okay, so it's just one thing to get started. You can sort of get your head around what this technology is doing, what the possible use cases are, and then think of other use cases. And then one of these ones, I forget which one it is, somebody says, oh, there's a use case that everyone talks about, but we just have not had time to work on. And it's related to loyalty or reputation. So the idea would be that I could prove, so there's different contexts where you might want to do it. So loyalty is kind of like, think about like air miles or something like that, okay? Every time I say buy something from a store, I get a receipt, it's emailed to me. I now have a proof that that was sent to me. What I could do is I could go through all those emails, I could pull out the balances of how much I paid, right? And then I could go to the business and give them a proof and say, I spent $100 in the last year or $1,000 in the last year with your business. And then maybe they have a loyalty program or something like that. So that's like sort of one example of what it could be done. Another thing is people are really, really concerned about the difference between human and AI agents, especially when you're like registering things. And so one way that you might prove that you're human, it doesn't prove it, but gives some evidence, is you could say, hey, I have this email account and it's been active for the last 5 years. I bought things on Amazon. I've done this. I've subscribed to this, and I have all this like really rich content in this email address. By the way, this email is tied to my government ID, so you could use ZKTLS to do that. And so I look like a human, right? That's really hard to fake. People can go register a fake email. They could maybe buy stuff on Amazon, but they're probably not going to spend a lot of money like building up an identity like that. And so if I can sort of pull all of that stuff into like a short, think of it like a digital driver's license, right? It's like a proof, and it just proves a bunch of facts about me, then that could be a potential way of the type of thing that you might show to prove that online that you're a human and not an AI agent kind of thing. Okay, so there's some other podcasts here. These are links just to podcasts. One's sort of about loyalty, and the other one's about telling the difference between AI and humans. These are not zero knowledge specific, but they come from that realm of cryptography and blockchain and things like that. And so I'm sure that ZK comes up at some point in these podcasts, but they're not necessarily focused on ZK specifically. Okay, questions about the project? Okay, so short term, you should try and listen to this. You don't have to listen to these, by the way. It's just, they're suggestions. You can Google it. There's transcripts for them. You can copy paste them into ChatGPT and say, explain it to me, however you want to learn what this stuff is. But in the short term, like in the next week or 2 weeks, you should try to wrap your head around what this stuff is, so then you can have time to start thinking about what are the applications in order to do a potential project. Okay. Questions? See none. Okay, so then we'll move to the lecture itself. Okay, so now what I would like to do is, over the next many weeks, try and teach you how one zero-knowledge system works. Okay, so a zero-knowledge system is something where I have a circuit, and I'm going to show you the output of the circuit. I'm going to show you what the circuit looks like what the gates are and everything about it, but I'm not going to have you execute the whole circuit. I'm either just going to prove to you that the output is right, or the alternative will be is sort of there'll be some inputs to that circuit that are secret, that I'm not disclosing to you, and I'm going to prove that I know some inputs, and if you fed them into this circuit, this is the output that you would get. Okay, so that's what zero knowledge is. Now, zero knowledge is going to basically I'll draw this slightly different because this will be a better roadmap. Okay, so these terms won't mean anything to you, but it will. It's something that, like, toward the end of the course, you can come back to sort of see why we were doing everything. So my ultimate goal is to teach you one system. It's going to be called Planck. Planck effectively has two things that go into it. The first thing is the only thing from cryptography. We don't need anything really that fancy from cryptography. What we need is something called a commitment scheme. And for Planck, we're going to have something called a polynomial commitment scheme. So it's a special kind of commitment. So that's the first thing that I will do. Okay. The other component is we're going to have this like back and forth. I'm going to have a circuit. You're going to ask me questions about it. I'm going to answer the questions about it. And at the end, you're going to be convinced of whatever it is I'm trying to prove, that I know these inputs to the circuit or the output is correct. Okay. So that back and forth we call an interactive oracle protocol. It sounds complicated. Interactive is just this idea of you're kind of going back and forth. Oracle is this, like, somebody knows, the prover knows everything about it, and then protocol is just like you have a prover and verifier. Now, at the end of the day, we're not going to make it interactive. We have a way of making it non-interactive, so I can just give you the proof, I can show it to you, you can show it to whoever you want, and that proof holds. You don't have to come back to me and talk to me about it. But before we get there, we'll describe it first in an interactive form. And because we're doing Planck, which is based on polynomials, it's going to be a polynomial version of that. So it's called the polynomial interactive oracle proof. Okay, so we're going to need a little bit of math, like I said, in order to do both of these things. So the one thing that both of these have in common is they both use polynomials. So next class, not this class, I'll go over the basics of polynomials, okay? We are talking about high school polynomials, okay? So think of something like, you know, a0 plus a1x plus a2x squared plus a3x cubed, that kind of thing. Not complicated, there's not multiple variables. And we're actually going to make our lives easier because we're going to say these can only be integers, okay? No decimals, no complex numbers, nothing like that. And we're also going to limit how big the integers get. So once they get too big, we're going to kind of, you'll see it today, we have a thing to reduce it down called a modulus. So I'll just write this here. Okay, so, but anyways, we'll go over what a polynomial is, what does it look like, if you have a bunch of points, how do you draw a polynomial through the points, and all of those kinds of details and stuff, okay? And then the commitment part of this, so this corresponds to the polynomial part of polynomial commitments and obviously corresponds to the polynomial part of IOP. The commitment part, what we need is we need a basic result in cryptography called the discrete logarithm problem. If you've taken 6110, you will have seen this. In today's lecture will be a review for you. If you haven't, don't worry, we'll go through it, okay? So the DLP is, it's kind of like a hard problem that no one knows the solution to, and we use it in cryptography to provide security. So for example, let's say I want to hide a message. I might use this problem to sort of encode my message, and then I'll send it across the wire, and no one can break it, because they would have to break this problem in order to read it. Okay, and this also works in this setting of mod q. Okay, so the integers mod q, which is something I'm going to spend a bunch of time on today. And this, by the way, is called number theory. So that's the branch of mathematics it comes from. So today we're learning number theory. Okay, but number theory just means the study of numbers. Okay, so we're just going to look at numbers and how they behave under multiplication and addition and exponentiation, and we're not going to pull in all of number theory or treat it like a really complicated thing. We're just going to look at exactly what we need to know, but technically we're doing number theory. So can you say it louder? Sorry.
Okay. Are we going to learn DLP in detail?
Yes, sort of. You're going to learn what it is, and then it depends on what you mean in detail, but you will. I'll show you two algorithms for solving it. So we know how to solve it, just we can't do it fast enough. And yeah. Okay, so let's just jump into this modulus thing. So I'll call it a modulus. How many people have taken 6110, by the way? Okay, 1, 2, 3, a couple, okay. Yeah, okay, so about half of you. Okay, so let's say I have an equation. I'll call this C. So C equals A mod B. Sometimes we write equal signs funny because it's a modulus, but we're just going to ignore that for now. Okay, so what does this mean? A mod B. What this means is you do A divided by B, okay? And normally, you might get like a decimal, like 4.3333, okay? So you have 4 wholes, and you have 0.3333, that's like partial fills of it, okay? And that's called the remainder, okay? So if you want to write down an integer division, if you want to divide 2 integers, you could say it has this many copies of B, and then there's this that is left over, or the remainder, okay? So it's A divided by B, and we keep the remainder and we throw away everything else. Okay? Sometimes we divide it and we throw away the decimal. Okay? This is sort of the opposite. We divide it and we just keep the remainder. Okay? If you kept both, how many times it divides it, and you kept the remainder, then you've kept all the information that you need about it. So then you know the complete division of something. Okay? So a simple example that we use every day in life is a clock. So I'm going to draw it a little weird. Normally we call the top position 12. I'm going to turn it to 0 because it will work better for the math. How many positions are there in a clock? 12. Okay. So if we want to do clock-based math, we're going to consider a modulus of 12. Okay? So we're going to work in mod 12. Now, a number 2 or 3, actually, let's just go through this. This may be helpful. What is 2 mod 12? It's 2, okay? So the first thing about mod is if you see any number between 0 and 12 minus 1. So 12's the sort of the number that we're not quite reaching. Okay, so the mod here is 12. So we go to 11. We'll have 11, but we won't have 12. Notice how many integers are this? How many integers are these? 12, right? Okay, so we have 12 integers starting at 0. So that's 12 to 11. Okay, so any number that's already in that range, if you mod it by 12, it's not going to change it. Okay, so in general, if you mod by a number that's bigger than the number that you are, it's not going to change that number. The only time it's going to change that number is when it's bigger than this range or smaller than this range itself. Okay, what's 14 mod 12? 2. Okay, so if you know 24-hour clock, you know that 14 o'clock is the same as 2 p.m. And so why is that? Well, I did 14 divided by 12. Okay, so let me do it like this. So 14 divided by 12 is 1, and remaining I have 2 12s left over. Okay, so I have 1 whole 12 in there, and then I have 2 12s remaining. Okay, and I'm just keeping the remainder. That's the definition. Keep the remainder. So this number is what I'm keeping, and so this is going to equal 2. What's 12 mod 12? 0. Okay, so if I do 12 divided by 12, I have 1 whole, and I don't have any remainders left. 12 over 12 is 1, so I can set that to equal to 0. Okay, does that sort of make sense? Okay, so let's say it's 10 o'clock, and I say, meet me in 5 hours. That's 10 plus 5. Right, 5 hours from now, mod 12. What time are we meeting? Okay, 3. So 10 plus 12 is 15. Sorry, 10 plus 5 is 15, mod 12. And then if you divide it out, you'll see that you have 1 12 over 12. Plus you have 3 12s left over, so it's going to equal 3. Okay, questions about this? Okay, what if I give you one more example, and then I'll write down a rule. What's 10 plus 12 mod 12? 10. Okay, So if I ever add the same modulus to itself, think of a clock. If I add 12 hours, it just goes back to where it started. If I add 24 hours, it's going to go back. So actually any multiple of 12, if I add it, it's going to do nothing. It's going to cancel out. It's going to equal 0. Okay? Mod is distributive, I think is the right term. So 10 plus 12 mod 12 is the same as 10 mod 12 plus 12 mod 12, all mod 12. Okay, so you can do the modulus at any time. Okay, so if you have a big expression, you have a bunch of numbers, you have to add them together or multiply them or whatever, you can take the mod at any point. You don't have to wait till the end. Okay, and every time you take the mod, you always get a number that's between 0 and 11. Okay, so sometimes just from a computing standpoint, if you're going to compute a modulus on a big expression, what you want to do is you want to take the mod all the time so that your numbers are always staying small. Okay, so if we apply this, what's 12 mod 12? We have it here. It's 0. Okay. So this is, and what's 10 mod 12? It's 10, right? Because it's less than 12, or it's less than 11 anyways. So it's 10 plus 0, so it's going to equal 10. Okay? So I can simplify it first, before, yeah. Or I could do 10 plus 12 is 22, and 22 mod 12 will give me 10. Okay, but the point is I can mod it down right away, so I can immediately see that this is 0, and so you don't have to wait till the end to mod it if it makes your life easier. Yeah.
You know the last mod at the end?
Yeah.
Is that necessary to have in this equation?
Yeah. So good question. So do we need this at the end? So what I can tell you is that this number, because I do the mod here, it's never going to be bigger than 11, and I can tell you that this number is never going to be bigger than 11. But could you have two numbers that are less than 11 that when you add them together would result in something bigger? You could, right? Yeah. So that's why we do need the mod at the very end. Okay, so if we want to think about, let's move away from mod 12 specifically. And we'll think about things in general. Actually, let me move to A mod P. We're going to spend a lot of time on this. Okay. What we're going to consider is, instead of mod 12, we're going to consider numbers where the modulus is prime. And the reason is there's some structure when you do prime that you're going to see. I'm going to show you what that structure looks like. Okay. But we'll consider it there. Okay. So the first thing is, if I have an equation like this, so I have A plus either P or some multiple of P. So this is any integer. Okay. What happens is that any copy of P is just going to go to 0. This xp term will go to 0, okay? So again, it's like if I have a clock, a time, and I add 12 hours to it, it doesn't change the time. If I add 12 hours, if I add 12 hours twice, still isn't going to change the time. If I add 12 hours 100 times, it's not going to change the time, okay? So x is the number of times I'm adding p to this number, but because it's mod p, because I'm adding p mod p, it's just going to equal A. Okay? So adding multiples of the thing that you're modding by doesn't change the underlying integer. Okay? All right, so this is like a rule that we will use at some point. The second thing I'll do is I'll try and give you a visualization. Okay, so now I'm just going to switch gears, and I'm going to give you a concrete example. I'll keep p very small, but I'm going to pick a prime number 23. Okay, so just to be concrete, I'll give you a concrete example. So prime 23 is a prime number. You can think about that and verify that for yourself. And so let's consider we have a bunch of numbers like this. Here's the number 0, okay? And on the top, we'll draw numbers, we'll call them A, and on the bottom, we'll think about what it is, A mod B. And here, I'll be specific, and I'll do A mod 23. Okay, so the number 0 mod 23 is 0, okay? The number 1 mod 23 is going to be 1. Okay. I can go all the way up to the number 22. 22 is 1 less than 23, and it's still going to be exactly the same. Okay. So all of these numbers are exactly the same. What happens when I go to 23? Say it louder.
Say it's the same as 1.
Okay, you're close.
So as 0.
As 0, yeah, thanks. Okay. So what's going to happen is it's going to go back to 0. Okay? Okay. Then if I go to 24, what happens? It's going to be 1. And so what I'm doing is I'm actually just counting down here. So I go 1, 2, 3, all the way up to 22. I hit 23. Sometimes we call this informally a wrap, so that it's like the integer wraps around, goes back to 0. And then if I keep counting, it just keeps going up by 1, okay? If I go up to, say, 44, which is 22 times 2, right? Actually, let me go to 46, which is 23 times 23. Then I'll go back to 0, okay? So as I go up this line, I'll go 0, 1, up to 22, then I'll wrap, I'll go 0, 1, up to 22 again, I'll wrap, and I'll keep wrapping all the way up, okay? What if I go to -1? Say it louder. Same thing, meaning what? Is going to be, I just can't hear you, that's all. Yeah, so it's going to be the same, but what's the number that I write here, is what I'm asking. Yeah, so what is -1 in modulus? Okay, it's going to be 22, okay? Okay, so again, I went to 0, 1, 2, 3, 22, and then I wrap, I go back to 0 and I count. So whatever the copy of this integers are, right? The next set of integers will have the exact same copy. The next same integers will have the exact same copy. And same thing before, okay? So I'm going to have a 0, and it's going to go up to 22. It's going to be the last number before I hit 0. I add 1, what's -1 plus 1? I go to 0, then I wrap back, and I go back to 0 itself, okay? So we can talk about negative numbers. There's one application of zero knowledge that I'll show you at some point in this course where we care about the difference between a positive and negative number. But technically, when you work mod something, there is no true negative number, right? Like a -1 and a 22 are the exact same number, okay? So there's no real concept of a negative number. We have conventions where we sort of say everything that's sort of halfway between the top half of the group and the bottom half of the group, we call these positive and these negatives, but I'll introduce that later when we need it, okay? But I just want you to see what this looks like, okay? Now, another thing that you can think of just more from an implementation standpoint is think of this as a number line And so we have a bunch of numbers on this line. Okay? Any numbers that are inside this interval will map to the same number inside the interval. Okay? And numbers that are outside, they're going to map into the interval somewhere. I'm not keeping track of exactly where, but they're all basically going to map inside here. Okay? So if you see mod 23, what that means is you can make, A can be any number in the world, any integer. Okay? It can be really big, it can be small, it can be big negative, it can be big positive. But once you apply that mod 23, it just goes into a number, a small interval. It's going to be, the result is going to be some number between 0 and 22. Okay? And so in cryptography, we use this to sort of keep control over numbers. Okay? Because when we do additions and multiplications, exponentiations, numbers get big fast. Okay? So what we do is we use the mod to just bring them down so that they're always in that interval. So we're never dealing with numbers that are bigger than that interval. Okay? All right. So is it a complexity? Does it make your life harder or does it make your life easier? Okay? So the answer is twofold. It makes it easier in a sense that you're always dealing with smaller numbers. Okay, so in terms of thinking about things, it makes it easier. But one thing that makes it harder is there's simple operations that you can do. And if you do them on the number line, you can write down, you learn in high school how to do like certain operations. An operation I'll give you an example of is a logarithm. So we know how to do logarithms. You have a button on your calculator. Okay? But if you do a logarithm with numbers here, all of a sudden that algorithm that your calculator is using, the button on your calculator, it doesn't work so well anymore. Okay? Because all these numbers are getting, they're all getting mapped into this small interval. Okay? And it doesn't work that well. And because it doesn't work that well, that's what we're going to use for cryptography. Okay, so by working mod P, what we're doing is we're taking some easy things and we're making them hard. And because they're hard, we're going to leverage that in order to do encryption. Okay, so that's just sort of a guideline of where we're going. Okay, here's what I want for cryptography. What I want is a group of integers. I'll call it G. Okay, so this is a group. I'll define it in a second. For now, just think of it as a set of integers. So it's a subset of integers. So I don't want to use all the integers. I just want a subset of them. Okay? And I want to have Q of them where Q is a prime number. Sorry, prime. So a group of Q integers. Okay? And part of the definition of a group, well, there's different kinds of groups, but we're going to, I could be more specific, but I want multiplication to work. Okay? So I want to be able to take two elements of the group. I want to multiply them together. Okay? Then I'm going to get another number. And what I want also is I want it, so I want all the rules to work of multiplication. All the rules that you're used to, like, let's say like, A times B plus A times C equals A times B plus C. Like all that kind of stuff. I just want that stuff to all work, okay? And the second thing I want is I want it to be closed under multiplication, which means if I have group element A and I have group element B, I multiply them together, I get some result C. I want C to be in the group as well, okay? So I never want to leave the group. I just want to multiply these numbers together and never have to leave the group, okay? Another property of a group that I need, it's sort of non-obvious, but I need an inverse for every element. Okay. And so I want, if you have some number A and it's in the group, sometimes we write this weird E, just means it's a member of the group. So if A is in G, then there exists some B in the G as well. Okay, so there exists some B, there's some other B in the G, such that A times B equals 1. That's what an inverse means. Okay, so here's my first guess at what I could do with a group. Is I'll define GQ. Okay, actually I'm purposely saying Q, and here I was talking about P, and they're both prime numbers, and there is going to be a relationship between Q and P that I'm going to get to, but for this example, I'm just actually going to go back to the example of P. So I'm going to define a set of integers, which is just P, 0, 1, 2, 3, all the way up to P minus 1 for whatever the prime is. So in our case, we were thinking of P equaling to 23. So in this case, it would go up to 22. Okay, and I'm going to call that my set of integers. Okay, and I want to know, do the rules of multiplication and all that work if I just do this? Okay, so this is the integers mod 23. So that's how we might describe it. And in math notation, when I talk about the integers, I have a fancy way of describing it, which I call Z. Okay, so Z is a funny Z. It's the set of integers. And then if I want to say it's mod 23 or mod P or whatever, I just put 23 down here. Okay, so this is just notation for it, but it just means the integers from 0 to 22. Okay, yeah. So you have no answer to that question yet. So trust me that we want to limit ourselves to prime numbers. And I'm going to show you in about 10 minutes the structure that you get when you use prime numbers. Yeah. Okay. All right. First off, does 0 have an inverse? It doesn't have an inverse. Okay. So there's no inverse. All right, I want an inverse. So I want my group to have an inverse. I want every element in my group to be invertible. So this isn't going to work. I already can tell you it's not going to work because it has 0. Okay. So the next thing I could do is I could just drop 0. So let's use the exact same group, but I'm going to get rid of 0. So I'm going to do 1, 2, 3, all the way up to 21, 22. Okay. And this is used so often that there's actually a special notation for it. We add a star to Z. So Z means 23. Z star means excluding 0. That's what it means in practice. Technically, I think it means every element is invertible. So all the elements in Z23 that are invertible, but that is for our practice, for practical purposes, it's just 23. That's it. Or sorry, it's just 0 that we exclude. So yeah. Okay. Now, when you first learn cryptography, if you take 6110, you might use this group. Okay. It's not actually secure for reasons that are already on the slide, which is I said I wanted a group of Q integers, where Q is a prime number. How many integers are there here? Try again. Sorry? Yeah, but what is that? What is that? If Q is 23? There's 22. Yeah, okay. So and you can see, you can just count them off. Yeah, you're close. There is Q, yeah, anyways. Okay, this is 22 integers. So the size of this set equals 22. 23 is a prime number. Is 22 a prime number? It's not, okay? So also this group's not going to work for me because I want this to be prime. Okay, so it's not prime. Okay, but we're getting really close to something. Okay, so I'm going to show you how we get both of the things that we want. And the answer is that we're actually just going to not use all of these integers. So we have 22 integers available to us. What I'm going to do is I'm going to select maybe half of them, and I'm going to call that my group, and I'm going to convince you that it has all the properties of multiplication and it's closed under multiplication and all that type of stuff. Okay. All right, so let me show you like visually what's going on first. Oops. Try and keep this fit on the screen. Okay, what is this? What are we looking at? What this is a multiplication table, right? You remember in high school you had to memorize the multiplication tables maybe for numbers between 0 and 9. So it's a multiplication table. The only reason it looks a little different, if you look here, you'll recognize it probably as a multiplication table, right? Okay, even if you go up to here. But then when you get up to here, it starts to break down, like this 2 seems out of place. Okay, so why is this different than a normal multiplication table? Well, it's mod 23. Okay, so if I want to know what is 6 times 15 mod 23, I can use the table. So I start at 6, I find 15, and my answer is going to be 21. Okay? All right, so this is a multiplication table. Now, the first thing I want to ask you is every number invertible? Invertible means that there's some other number, and if you multiply it by that number, you get a 1. Okay? So I'll tell you the answer. The answer is yes, every number is invertible. But looking at this table visually, can you show me why that's the case? Like what is it about this table that would prove to me that every number is invertible?
Even number of numbers.
Okay, not that.
In each row you will find one.
Sorry?
In each row you will find one.
Okay, great. Yeah, so in every row, there's a 1 somewhere. Okay, so here, I can find a 1. In this row, I can find a 1. In this row, I can find a 1. Okay, and also each column, if you want to think about columns as well, you can find a 1. Okay, what's the inverse of 8? It's 3. Okay, so why is it 3? Because 8 times 3 gives me 1. Okay, so if I ever want to find the inverse of something, I go along the column, I find the 1, and then whatever the other number is 1. Okay, so if the inverse of 8 is 3, what's the inverse of 3? 8. Okay, so it better be the case. So if there's a 1 here, if we go here and we go up to 8, you'll see that there's an inverse here. Okay.
What's the name of this table?
I just call it multiplication table. That's it. Yeah, there's no special name. It's the only difference is it's mod p. That's the only thing. Okay. Let's say in general I have number a and I multiply it by b. It equals whatever it equals. If a times b equals something, what does b times a equal? Same thing. Okay, that's one of the rules of multiplication, right? Order doesn't matter. What does that mean in this table? What that means is that the shape of this table is, we call it symmetric in the diagonal of the table. So I'm going to draw out the diagonal of the table as best as I can. okay? And so let's say there's a number here, the same number is going to be here, okay? If there's a number 16, I go across the diagonal, there's going to be the number 16 here. If I find this number 2 and I go across the diagonal, I'll find the number 2. Okay, so it's an exact copy of the table. That's because A times B is the same as B times A. Okay? So with a table like this, you could work out more complicated expressions, but what I'll tell you is just that multiplication works the way that you would expect it to work. Okay? And because we're modding by 23, all the numbers in the table are no bigger than 23. Like we never leave 23. We never see any numbers bigger than 22, I should say. Okay? So yeah. Okay, that's the multiplication table. Now the next thing I want you to consider is an exponentiation table. Okay. So what this table represents is it represents whatever the number is in the row raised to the power of the number in the column, mod 22. Okay, so it's row to the column mod 22. First off, what does exponentiation mean? If I have r to the power of 3, what does that mean? Sorry? Sorry, mod 23, thank you. Yeah, thanks. Okay, I have some number, let's say 12, 13. 13 to the power of 3 is the same as 13 times itself times itself. That's what exponentiation means, okay? So whatever this number is up here, I'm just multiplying it by itself that number of times. That make sense? Okay, all right. So just remember that. It's sort of an obvious point, but it's something that we can do. So let's just check that. So let's say I do 12 to the power of 3. Then answer is 3, okay? So 12 to the power of 3 mod 23 equals 3. Okay? So that's how I read this table. Could I get that same result from my multiplication table? I could, but it would take a couple steps. But I could do literally what I just said. I could say that 12 to the 3 is the same as 12 times 12 times 12. Okay? What's 12 times 12? So 12 times 12 is 6. Okay, so this would be 6. So that would take care of these two 12s. I still have to multiply it by 12 again. What's 6 times 12? 6 times 12 is 3. Equals 3. Okay, which is the result that we got from this table itself. Okay, so this table is nothing special. It's actually doing everything that everything you need, everything from this table is in this table. It's just you have to multiply things by themselves. Okay. How many times do we have to multiply something by itself before it goes back to just being what it was? Okay. If your name is Fermat, very famous mathematician, you'll have the answer to that. If you're not, you don't know the answer to that. It's not something that you learn but there is an answer to it. Okay. So it's called Fermat's Little Theorem. And actually, before I get there, I'm going to define something that's related to it that we'll see. I'm going to tell you what the... Okay, I'll show it to you visually, and then we'll write down the math for it. Okay, I'm going to pick one of these rows. Let's start with 6. And I'm just going to scan along this row. Okay? As I scan along this row, what do I see? I see 1, 6, 13, 9, 8, 2, 12, 3, 18, 16, 4, 1, 6, 13, 9, 8. Do you notice anything about, did you see a pattern there? It repeats. Okay? So I go 1, 6, blah, 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 blah. Then I repeat, and I do the exact same pattern. Okay, if I kept going, so this shows you the exponents just from 0 up to 22, but if I kept going to 23, 24, 25, what do you think would happen? It's going to repeat. Okay, it's just going to keep repeating forever. Okay, let's pick another row here. Does this row repeat? It does. Okay. Whoops. Let's look at the last row. Does the last row repeat? And finally, let's look at this row, 5. Does it repeat? No, except for here, but if you could see the rest of the table, it will repeat, but basically it doesn't repeat, okay? So you actually get something that looks like this. What's the first integer you see at the start of a sequence? So something's about to repeat. What's the first integer that you see as the next one? 1. It's always 1. Okay? So every number, when you exponentiate it or just multiply it by itself, what it's going to do is it's going to cycle through a bunch of numbers. Then it's going to hit a 1. Then it's going to repeat. Okay? And it will keep repeating. So you can keep multiplying it by itself. Okay? So we call this a multiplicative cycle. Okay? So you just multiply it by itself. Hits the number 1 eventually, then you know it's about to repeat. Then what's the next number after 1? You get the number itself. Okay, so if you're multiplying 10 by itself, 10 times 10 times 10 times 10 times 10, eventually you hit a 1. And then the next time you multiply it by 10, obviously what's 10 multiplied by 1? It's 10 itself. Okay, so you always have this pattern where you have a 1, then you have the number, then you have some other stuff, I don't know what that stuff is, and then it repeats. Okay? All right. How many numbers are in this block before it repeats? In other words, how many unique numbers do we see? If we start at 6 and start multiplying it by itself, how many unique numbers do we see? 11. Okay, so this has size 11. Okay. What about 5? 22. Okay, so this one has 22. What about 22 here? Has size 2. Okay. What about 1? Does this repeat? So it repeats every 1. Okay, so we have size 1. Okay. So we have different sizes. So the size of it until it repeats is going to be different. It depends on the integer itself. Okay. So we have a name for that, which we call the order. Or multiplicative order, because we're generating this with multiplication. Okay, so how many integers until it repeats? So here I'm just going to make a little table of orders. So the order of 1 is 1. The order of 2 is, it starts repeating here. So that's size 11, so it equals 11. Order of 3 is 11. Order of 4 is 11. Order of 5 is 22. Order of 22 is 2. Okay, so different numbers give us different orders. Okay, yeah. Sorry, you'll have to say it louder. I still can't hear you, sorry. Yeah. Why is order 2 11? Yeah, so the number in here is the row, okay? So when I say order 2, what I mean is find the row number 2, yeah? And then the reason it's 11 is because I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, then it repeats. That makes sense? Yeah. Okay, so if we want to sort of mathematically say what this is, we can say it's the smallest value t such that g to the t equals 1 mod p. Ignoring t equals 0, because everything raised to the power of 0 is 1. Okay, so this is just, it's what you understand, it's your intuition of like you just go along the row until you hit a 1, but it's just the mathematical expression of it. Okay, okay, so let me show you Fermat's little theorem, and then so you might have heard of Fermat's last theorem. It's a more famous one, but this one's less famous. Okay, it basically says if I have a number, a row, so this is a row in my table, eventually we're going to start using the term G to represent it. G means generator because it's kind of like generating integers. It's generating a sequence of integers. But anyways, so if I have a number G and I raise it to the power of p minus 1, mod p, what do I get? Okay, so let's try and solve this graphically. Okay, so let's say that p is 23. What is p minus 1? 22. Okay. So if I look at this table, what is any number raised to the power of 22? 1. Okay, and why? Okay, so it's this column here. So what I'm doing is I'm starting with any number I want, I raise it to the 22, and the result I get is always 1. Okay. All right, so what does this tell us? If we put these two things together, we basically say the order of something is basically run it until you hit a 1. And then Fermat's telling us that the last column always has a 1. Okay? What that means is that we're always going to wrap. Okay? There's not going to be some weird number that keeps going on forever. Okay? It's eventually it's going to hit the last column and it's going to hit a 1, but it might have hit it sooner. Okay? So some of these numbers hit a 1 sooner, right? But you're at least going to make it all the way to the end. Then you're definitely going to hit a 1. And when you hit a 1, you're going to wrap. So the biggest order that we can see is 22. Okay? We're never going to have an order that's bigger than 22 if we're working mod 23. It makes sense? Questions about that? Okay. All right. All right. So if we put this together, then so if I do G mod P, I'll do G to the X mod P, then the order of G will be less than or equal to P minus 1. So that would be 22 in our working example. Okay, now, could you have an order less than 22? You can. We saw it. Okay? At this point, it's maybe worth actually going through every single number in this table and seeing what the order is. So I'll do this in red. I won't use red yet. Okay, what's the order of 1? What's the order of 2? 11. What's the order of 3? Just, okay. Then we go out to 22. Then we're going back to 11. Then we go to 22. Do 1, 1, 1, 1. These ones are out here. And then what's the order of the last one? It's going to be 2. Okay, so I have one thing of order 1. I have one thing of order 2. And I have, sorry, here I should technically circle this because we said 0 doesn't count. So that's why it's... Okay, so I have something of order 1. I've seen something of order 2. I've seen something of order 11. And I've seen something of order 22. And that's it. There's nothing order 17. There's nothing order 3 or something like that. Okay? Why is that the case, do you think? Is there something special about the numbers 1, 2, 11, and 22? Okay, let's say that, for example, there's no number like this, but pretend there was a number that, had, like, say, 7. Okay? So just pretend, this doesn't make sense, but pretend that this was like the set of integers 7. Then the next number would have to be a 1, right? Because that would be the start of my next group. So then I would circle 7 numbers, 1, 2, 3, 4, 5, 6, 7. So I have a group here. Then this number would have to be a 1. Then I would go 7 numbers, 1, 2, 3, 4, 5, 6, 7. 6, 7. And I managed to pick a terrible example to use. Okay, I know why I did this wrong. Yeah, so what I did is I copied, or sorry, I started at, I included the 1 at the start. Is that why I did it wrong? Okay. Let me just try this again. Let's say.
No, we should stick a one guy using 0. That's why.
Sorry. Say the.
Because it is under 0 and we're not inserting 0, so we should start from 11 for the.
So I sort of agree with you, but because when we wrap, we start the next one at 1, we should include 1 in our first set. Yeah. I think I must have just counted wrong or something. But I'll just grab these integers. Okay, so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we'll say we have a group of 10. Then the next group of 10 would be like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it would include this. And then the next set of integers would look like this. Okay, so let's just assume that there was a group that looked like this. What's the first integer in every group? 1. Okay, so this would be a 1. This would be a 1. Okay. If 1 is the first part of the group, can it appear anywhere else in the group? It can't, otherwise it would be a shorter group, right? As soon as you would hit it, it would be shorter, okay? What is Fermat's, so can this number be a 1 in this theoretical group? Okay, we have a 1 and we have something, so this cannot be equal to 1. What does Fermat's little theory say?
You have to have one somewhere.
It says that the last column, every number has to be 1. I actually didn't finish writing the theory down. Okay, so that's a contradiction. Okay, so there's no, that group size is not possible because it wouldn't result in a 1 there. Okay? Visually, can you tell me how big the groups have to be so that I get a 1 at the end? Okay, it has to be a division of the size. Okay, so either I use all the elements, then it goes to 1, or I divide it, say, into 2. Then I can have 2 full copies, and then I'm ready to hit a 1. Then if I could divide by 4, I could have 4, right? If I can divide by 2 or whatever, okay? What is the number I'm dividing by? So the biggest group is 22, right? Half of 22 is 11, okay? So I'm dividing the number 22, okay? So I start with the number 22. I'll have some things that are order 22, and I'll have things that are every divisor of 22. Okay? So what that means is I see the number 22. Half of 22 is 11. Okay? What's half of 11? Okay, is that an integer? Okay, so there's no integer that's going to divide 11, so then I'm done. Okay? All right. Okay, so okay.
Assume is only valid if B is small.
Exactly, yeah. So then this is the question that was earlier. Why are we always working mod P? Okay? The rule I just told you holds mod P, but it doesn't necessarily hold for any other modulus. It might happen to hold, but I can guarantee you that it holds. That's where the number theory would kick in. They would prove that anytime you have a prime divisor, it always holds. Okay? Sorry, a prime modulus prime. Okay? So in this class, we're not going to worry about what happens in other types of things. If you take cryptography, you'll see another setting, which is the multiplication of 2 primes. So RSA is an example of something that uses it. So this doesn't apply to RSA, okay? But it's going to apply to us, okay? So it's going to cover the integers mod P and any other thing that's set up with a prime set of numbers, okay? So if you have some group of numbers, that group is prime, and you have an operation that's like multiplication that you can repeat on itself in order to exponentiate, then you're going to have the same properties, okay? So there's a second setting that's a lot more efficient called elliptic curve cryptography. And in elliptic curve cryptography, it's the exact same. Everything works exactly the same. The only difference is instead of these being integers, they're points. So it's an x coordinate and a y coordinate. And when I add 2 points together, or repeatedly add a point to itself, that looks a little weird. There's some algorithm for how you compute that. But other than that, it's going to behave exactly the same, okay? So those are the 2 settings that we tend to use. But this is definitely the easier of the 2 to see. Okay, so given a prime P, the order of G mod P will divide P minus 1. Okay? Not only it will, that says that, okay, because 11 divides P, it could be one of the things. It's even stronger. It actually says there must be. So for every divisor, there is going to be some G such that the order is that, okay? So we can just strengthen this slightly and just say that for every divisor, some G in the group will have that order. Okay, to illustrate this, we're working mod 23. Okay. What's p minus 1? Equals 22. Okay. What are all the ways of dividing 22? Well, I have 1 times 22 equals 22. And I have 2 times 11 equals 22. And that's it. Those are the only divisors I have. Okay? And so what this tells me is that I should see something of order 1. I should at least see one thing of order 2. I should see some things of order 11. And I should see some things of order 22. And that's exactly what we saw. Okay? Why can't I keep dividing? So I took 22, I divided by 2, I hit 11. Why can't I divide it further? So 11 is not divisible by 2. Is 11 divisible by anything? Why not? It's a prime number, okay? So what I did is I hit a prime number here, and then I have to stop. Okay? All right, now this is on purpose. What I did is, when I picked 23, I didn't actually just pick any prime number. What I did is, I picked a prime number where if you subtract 1 from it and divide by 2, you get another prime number. Okay? So that's something that we call a safe prime. So a safe prime means p is prime and p minus 1 over 2 is also prime. And if you just sort of move the p to the other side, we can call this q. And if we move this around, we also see p equals 2q plus 1. Okay, so that's just this equation, but moving the minus 1 over 2 to the other side. Okay, so we call this a safe prime. The smaller prime, the q prime, is called a Sophie-Germain prime. These are number theorists who discovered early, well, safe isn't a number theory, but Sophie-Germain is. So they found laws about prime numbers back in the Middle Ages, and so we name things after them. But the terminology doesn't matter. Okay, so in our case, 22, sorry, so p equals 23 is safe because 23 minus 1 over 2 equals 11, which is also prime. Okay, why do we care? I'm not going to tell you why I care. It's the same reason as why did we even start with prime? So that was the question. What if we do this with other integers? There's certain properties that hold when you work with primes that aren't necessarily going to work with non-primes. And when you work with safe primes, there's certain properties that are going to hold that work with safe primes that aren't necessarily going to work otherwise. Okay? So there's a lot of structure inside of this chart because I picked a safe prime to start with. And so for this course, you're just going to assume that you're always going to choose a safe prime. Okay? So from now on, we'll always choose a safe prime, and we'll be fine. Okay? Could you not do a safe prime? Yeah, probably. Okay, but you'll have to figure out, you have to make sure that things work if you're not using a safe prime that you wanted to use. But yeah.
What type of structure?
What type of structure? Yeah. Okay, so the first structure that we have is that we only have 1, 2, q minus, let's put it as 1, 2, q, and p minus 1. So those are the only orders that we have, okay? The second thing, give me a second, I'll show it to you, and it's something slightly different, but yeah. There's a second order, structure that's really important, but I just haven't quite got there yet. Okay, so what that means is if I'm using a safe prime, if I go back to this order thing, just I can write it now in terms of variables. So P, Q, 2, and 1 will be orders, mod P. Okay, and these two cases, 1 and 2, we call it sort of a degenerate case. The group that's ordered 1 will always be the first thing. Okay, 1 times 1 times 1 times 1 is always going to be equal to 1. And the thing that's ordered 2 will always be the last row. Okay, everything else in the middle will either be 11 or 22. It'll either be Q or P. Okay, it's going to be sort of random. Okay, so it's not going to be like 1 that's P, 1 that's Q, 1 that's P. There's not going to be any structure in terms of predicting when you're going to hit an order P1 and when you're going to hit an order Q1. Okay, if you can find that structure, right, and write it down, then you could break some number theory stuff. You might even be able to help out with some crypto algorithms. I have to think through the consequences of it. But in general, we don't know until we pick a number whether it's going to be order Q or order P minus 1. Okay, but as long as it's not 1 or 22, we know it's going to be one of those two things. Okay, how do I check, by the way? So I give you some number 16, and I want to know, I know already I'm working mod 23, and because 16 isn't 22 or 1, I know it's either P minus 1, so it's either 22 or it's 11. I just don't know which of the two is it. Okay, so visually how I do it is I scan along the row until I hit a 1. Okay, now a computer program can do that as long as this table fits on a slide. Imagine P is, millions and millions and millions of numbers, billions, even bigger than that. Like imagine that it's like 1,000 bits long, which is just a huge number. Okay, it's like 2 to the 1,000. It's more than the grains of sand on the earth. That's how big the P is. Is your computer program going to start at the start of the line and go along until it hits a 1? It's not going to be able to do that. It's going to run out of time. Okay, so what we would do instead is I already know what the value P is. I'll subtract 1 and divide by 2, so I'll get the Q. So I now know P and Q, and I'll just raise it to the power of Q. So I'll just check one integer. I'll say, is 11 raised to the power of Q 1? It's not, therefore it must be order P. There's no other option for it. Okay? Conversely, if I hit a 1, then I know that it's order Q. Okay? So that's how you would test whether something is order Q or not. Yes. Yeah, that's actually a great time. Thanks. Okay, let's come back at 20 after. Okay, so the very last thing I said before the break, I just wrote it out. So let's say I give you a number and you don't know what its order is, and I say, okay, figure out its order. But you do know that P is a safe prime, okay? Then basically you'll say, is it number 1? If it's number 1, you know the order is 1. If I give you the last element, which is P minus 1, then you know it's order 2. And if it's anything else in between, so it's probably going to be something else in between, you basically have two choices left. It's either going to end up being order Q, or it's going to end up being order P minus 1. If you want to check whether it's order Q, you just raise it to the Q and ask if it's equals to 1. If it raised to 1 equals 1, then you know it's order Q, and otherwise it has to be order P minus 1 because it's not 1, it's not 2, it's not Q. There's no other divisors of P because they're a safe prime, and because Fermat's theorem says that, then it's order P minus. It's order 1. Everything is order P minus 1 at least. Okay. So that's it. So you just have to do one exponentiation to check the order of anything. Okay. Now let me back way up. So I started showing you these things, and we were circling things, and I think we probably lost our way. I want to go back to what I wanted. Okay. What I wanted was I want a group of Q integers. Okay, so I want some set of integers I want it to be q integers big, where q is a prime number. So I want some set of integers, and the number of them is a prime number. Okay? And once I have those set of integers, I want to be able to do things like multiplication, and I want it to work the way that normally we think multiplication would work. And if I ever multiply these two things by each other, I want them to never leave that group. You stay inside of that group. And I want there to be inverses for all of those elements and things like that. Okay? So I just want a kind of like well-behaved group. Okay? So what is a group of integers that I could use? Do I have any sets of integers that are size prime number here? Okay, so 11 is a prime number, right? That's why I chose a safe prime. So I do have some integers that are, like I've circled some stuff in green where there's 11 integers, okay? So that could be the group that I use. So let's say that I choose this to be the group. 1, 3, 9, 4, 12, 13, 16, 2, 6, 18, 8, okay? So I just say that's my group of integers. I'm going to use those, okay? Now, the first thing I want you to notice is what's the difference between this set of 11 integers and say this set of 11 integers, which was a different number that also gave us order 11. So look at these integers and look at these integers and tell me what the difference is between them. Okay, so the order is different. Are the integers themselves different? Can you name one integer that's in this set that's not in this second set? They're the same. Okay? So all the integers here and all the integers here are exactly the same. Okay? I'm going to make a second copy of that because we scribbled over the other one. Whoops. And I just want to focus on this one exact point. By the way, someone asked in the break, it was a good question, if on an exam or something like that, would you get a table like this? I would. You would. So if I'm probably not going to ask questions about this because it's sort of basic, but and you also have a cheat sheet, remember, so you can always make tables like this. But. Okay, so this is again the same table. I just wanted a fresh copy of it. So this is row raised to the column mod p. Okay, so right now all I want to do is I want to focus on sets of integers of size 11. So what I'm going to do is I'm going to look at every integer that has order 11. Okay, so basically I'm going to look at, I'll draw it like this. So I want to look at this set of integers because it has order 11, then it repeats. This set of integers has order 11, and then it repeats. This set of integers does as well. Okay, as I'm drawing these, do you ever see a group of 11 integers that's different, other than the order, that actually has a different set of integers? Okay, so all of these groups of 11, not only they have the same size, they actually are the exact same group, right? If you think of a group just as a bag of integers, not like the sequence of integers, like the order doesn't matter, right? They're all the same. They're all the same integers. Okay. All right. So I'm noticing that all G generators with order G equals 11, which by the way is prime, are the same integers. Okay, so what do I see? I see 2, I see a 3, I see a 4, I see a 6, I see an 8, I see a 9, I see a 12, I see a 13, I see a 16, and I see an 18. Okay? All right. Now, next question. How many of those are there? How many groups of order 11 are there? So just count them. There's 11. Okay. So I have a bunch of groups of, or sorry, I have a bunch of integers that have order 11, and there's exactly 11 of them. Is that a coincidence? That is not a coincidence. Okay. That will always be the case if this is a safe prime. Okay. In a safe prime, you will always have q elements of order q, and there's going to be q of them, and they're going to have order q. Okay. Did I count wrong? 1, 2, 3.
I thought you were counting.
Oh, sorry. I think I didn't include 1. That's probably why. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Sorry, I should include 1. That was my mistake. Yeah. Okay. So the set is of size 11. Okay. So everything that I've circled, it always has some order of these integers. You don't see any other integers, and there's 11 of them in this table. The last thing I want to talk about, yeah.
So I'm also seeing on on the ones where the order is 22.
Yeah.
The 11th number is always 22.
Exactly. So that's another structure that you see. So here, when you don't hit a 1, the number here will always be a 22 instead as well. Yeah. So there's all sorts of patterns. And there's going to be a number theory rule that tells you why that's the case. Why, yeah. But anyways. Yeah. Okay. Last question I have for you is, what are the actual numbers that are generating this set of integers? Okay, so I've circled these sets of integers. What are the numbers that are generating them? So that's the numbers here, right? So 2 generates it, 3, 4, 6, 8, 9, 12, 13, 16, and 18. These are the numbers that are creating that sequence. What can you tell me about that set of integers? They're the same. Okay, so the set of integers that are generating these things of size 11 are the same integers that are being generated. Okay? So the generators with order 11 are the same set. Yeah. Sorry, with the exception of 1. That's right. Yeah. So what we're going to do is we're going to sort of patch 1 in as a special case. And so yeah. That's a good point. Thank you. Okay. So if we add 1 to the set of generators, then we in addition here, I don't mean like you add +1, I mean like you include, let me write inclusion instead of addition. It's probably a better way of saying it. Okay, so this is the structure that we were talking about with safe prime. So you have this group, and it has a certain size, and the number of things that are in the group are the same as the things that generate the group. Everything is nice and closed. Okay, what I'm going to do now is I'm going to take this table, and I'm going to get rid of everything that's not circled right now. Okay, so I'm going to give you a table where I just have the things here that are not circled, okay? Or sorry, that are circled. So I'm going to get rid of all the rows that aren't. I'll keep 1, and I'll get rid of the whole side of the table here. So it's going to be a smaller table, okay? Oh, by the way, before I do that, let me just say that this set of integers we call GQ. So that's the group that I was looking for, okay? So I'm going to use that notation. So GQ it's a group of 11 integers, okay? And it's going to be specifically the size, the group of these integers here. Okay? So what I'm going to do is I'm going to show you both a multiplication table. So I'll show you the multiplication table and I'll show you the exponentiation table. But in this case, I'm going to ignore everything that's not part of GQ itself. Okay, so I'm just going to do GQ. Okay, so this table is a strict subset of the two tables that you saw. Okay, so this is the multiplication table, and this is sometimes we call it a modular exponentiation, modular because there's a modulus involved. And sometimes we write mod exp as a short form for that. And so this is also modular multiplication. Okay. So I have multiplication. Let's start here. Okay. Is there an inverse for every element? How do I know? There's a 1 in every row and every column. Okay, so everywhere there's a 1 somewhere. So what that means is I can always find the inverse of an element if I need to do it. Is 3 times 2 the same as 2 times 3? It is. So again, this is a symmetric table, so you can see that elements repeat across the diagonal. So it has all those same properties. Okay, let's go to the exponentiation table. All right. Actually, no, let's go back to the multiplication table. Is there any number in this table that's not one of that group that I defined as GQ? Okay, so I have all the numbers of GQ on the column and the row. Is there any number in the table itself that's not a number of GQ? So it would take you a while to look at it, but you can see that there isn't. Okay, so everything in table is in GQ. Okay, so that's an interesting property. What does that mean? What's the meaning of that? What that means is if I have two numbers, A and B, and they're in GQ, okay, GQ just means I choose two numbers that are in this set of integers. Okay? I multiply them together, and then I take another out and multiply them, and then I exponentiate them, which is just multiplying them by themselves. I'm never going to leave GQ. I will always have, I will always end up with something that's in GQ. Okay, I can never leave it. Okay, so we say that this group is closed under multiplication. Closed meaning you'll never leave it. Okay, so you'll never see a number that's not in GQ. So as long as you start with numbers that are in GQ, the only thing you do with it is a multiplication or an exponentiation, which is just, it is a multiplication by itself, then you will always end up with a number in GQ. Okay, so you'll never leave it. Okay, so everything in the table is in GQ, so that means it's closed under multiplication. Okay, so let me, I'm going to write these out as kind of like facts about GQ. Okay, so the first fact is that if G is in GQ, then the inverse of G is also in GQ. So every element has a 1 somewhere in its row, and that's its inverse. So its inverse is never going to be, remember I deleted a bunch of this table here, so the inverse is never going to be, we already knew that everything here had an inverse, but now we know that it's also within the smaller table itself. okay? We never have to leave this table to find the inverse of something, okay? The second fact is that if, say, A and B are in GQ, then A times B will also be in GQ. Okay, so that's the closed under multiplication. Okay. What's the inverse of 1? I'm going to write inverse over here. The inverse of 1 is 1, because 1 times 1 is 1. Okay. What's the inverse of 2? 2 times what will give you 1 mod 23? 12. Okay, so 2 times 12 will give you 3 will be 8. 4 will be 6. 6 will be 4. Okay, I'll just write out this. Okay? What can you tell me about this column? It's the inverse. Okay? You see that? So here, 1, 12, 8, 6, 4, 1, 12, 8, 6, 4. If I keep going, I'll get it. Okay? So somehow, taking the inverse of something is the same as raising it to the power of 10. Okay? So that's another fact that we can write down, and we'll write it down in more general. So g to the minus 1, so the inverse of g, is going to be the same as g to the q minus 1. Okay. Now we can generalize this, and what we can say is that any exponent can be reduced mod q. Okay, so this is going to look weird. I'm going to probably repeat this maybe 4 or 5 times because it becomes important later. So there's something that we're going to see later called a root of unity that's related directly to this. But if I have a number like g and I raise it to the power of a, mod p, okay, what I can do is, if this a is really big, I can mod it down, but I'm not going to mod it down by p, because p is applying to like sort of this base case. What I'm going to do is I'm going to mod it down by q. So I could have a mod q, and then the whole thing mod p. Okay, so whatever's in the exponent, I can mod it down by q. So sometimes you're doing things in the exponent, like you're multiplying exponents together, or you're adding things up in the exponent. Whatever you're doing there, you could mod it by q first. You get a small number, and then you can do g to this small number mod p to figure it out. Okay, so the order here is q, and there's actually a very general. I think you can derive it from Fermat's little theorem. Which basically says that when you kind of go up a level, you go from p to p minus 1. So because q divides p minus 1, we set it up that way. You can do that. But later we're going to talk about this thing called roots of unity that's related to this, and then I'll give you a little more detail about the exact rules of why this is the case. But for now, I'm just going to state it as a fact. Okay? Now, let's go back to this. What's minus 1 mod q? So I have g to the minus 1. If I wanted, I could do mod q, mod p. Okay? Set that aside for a second. I have a clock. I add 12 hours to it. Does it change the time? Okay. If I add q hours to a clock mod q, is it going to change the time? No. Okay, I can always add q. If I'm doing mod q, I can add multiples of q and it doesn't change the time. Right? Okay, if you're not convinced, try and remember to an hour ago, where I said, if you have some number and you add p to it, mod p, or any multiple of p to it, you just end up back at the same number itself. Okay, so what that means is I can add q to this. It's not going to change the number, right? And so that's the same as q minus 1, okay? And that's what I wrote down. I said the inverse is the same as g to the q minus 1. And what that means visually is that if I want to find the inverse, I don't actually have to go searching for ones along the rows. Remember, if this table is the grains of sand on Earth, I'm not going to be able to scan along until I hit a 1. So what I'm going to do instead is I'm going to jump immediately to the inverse because I know it's going to be in this last column of the table. Okay.
So the mod P, is it different, like writing mod A mod Q and G mod P?
Exactly, yeah. So the exponents have their own modulus, and then the things that are down a layer have a different modulus. Yeah? And so we're eventually going to have to get comfortable with this idea. Yeah? And everything we do in Planck, by the way, we're going to do in the exponent. So everything we're going to do is going to work mod Q, and we actually never care about mod P. And in practice, what we're going to do is we're going to replace the base layer that we don't care about with these things called elliptic curves. But because we don't care about them, then everything in the exponent, even with elliptic curves, are still integers mod Q. Yeah.
So does this only work again with safe primes?
Again, so all of these things are true about safe primes. Saying that they're only true about safe primes is a little stronger, right? That means like there is no possible non-safe prime where this isn't true. I'm not sure about that condition, but there certainly are not safe primes or not primes at all where this isn't going to be true. Yeah. So more or less these things, they are guaranteed to be true for safe primes. If you're not doing a prime at all, they're not going to be true almost by definition, unless by chance. And then for things in between, some of them might hold, but some of them might not hold, or they might hold slightly differently. Yeah. So the fact that I'm using the number q here specifically is safe prime dependent. If I'm not working a safe prime, I can get this same fact, but I'm just going to change q to something else. But yeah. So for all of these purposes, assume, it's a safe prime. Yeah. So I'll just remind us of that. So 2q plus 1 equals p. Okay, so we can reduce exponents. So that's another sort of trick. And let me give you the general form of this. Now, I'll just write it down. We won't spend time on it, but I'll have to circle back to it like a lot later. So g minus 1 mod p. Actually, I'll write it like this. Okay. G to the a mod p is g to the a mod, and instead of q, what I can write here in a more general way is I can write the order of g. Okay, so we know that g has order 11. We set it up that way. Okay, so that's why it's q. So g, because g is in gq, it has order q. That's why we substitute q in. But if g wasn't in gq, it was in some other setting, then it will always be true that whatever the order of g is, you can mod the exponent down by. Okay, so again, you don't sweat this detail until we need it, which is way later. And then I'll go over it again and give lots of examples. Okay, there's a final fact, and this is something that is only strictly true about safe primes. It is very convenient, and when you move away from safe primes for efficiency reasons, you lose this property, And because you lose this property, a whole bunch of things get really hard in cryptography, but nothing that we have to worry about in this case, in this course, but other things that you do become tricky. Okay. All right, so look at this. This is GQ. Okay, so we have 1, 2, 3, 4, 6, 8, 9, 12, 13, 16, 18. Okay, that's the members of GQ. What I want you to do is I want you to consider this column. And actually before, just to make it a little more powerful, before considering that column, let's consider it in the big table. I want you to focus on the actual numbers themselves that appear in this column. Okay, what can you tell me about the numbers themselves that appear in this column? So I have a 1, a 4, 9, 16, 2, 13, 3, 18. Have we seen that before? It's the same group of integers. Okay, so this GQ, the set of integers we're using, appear in this column, and only in this column. Or sorry, there's nothing in this column that isn't in GQ. Okay, so one of the problems you have when you start doing cryptography in the very first place is you have to find a value G. You have to find one of the elements of the group. If you can find one of the elements of the group, then when you multiply stuff around, you'll never leave the group. Okay, but you need that first element. What's the first number I can start with? If I come to you and say, find a G value, right, for this group, right? You can do it by trial. So you can just say, is 1, does it have order 11? No, it doesn't. Does 2? Oh, yeah, it does. So I got lucky, right? The first thing I tried has order 11. But in some groups, you might try a whole bunch of things, and you haven't found something that has the right order yet. Okay? So what this property tells me is if I raise it to the power of 2, if I square it, I will get something in GQ. So if I want to find a random number in GQ, it's super easy. All I do is just pick a random number, I square it, and now I have something in GQ. Okay? So I don't have to go hunting for things in GQ. Okay? In other settings, when we move away from safe prime, that property disappears. We don't have an easy way. And so again, I mentioned elliptic curves. There's a big thing about like, how do you find something that's on the curve in the first place? Or I have a message, I want to hash it into an element that's on the curve. That's like really hard to do, and there's very complicated algorithms to do that. In this setting, it's super easy. All I do is I have a message. I either take the message or I take a short fingerprint of it called a hash. I square it, boom, I'm in the group already. So all I have to do is square it, okay? So anyway, we call these the squares of it, or the quadratic residues, if you want to use proper math terms. All right, so if there's some b such that a squared equals b, then b is in GQ. Okay, so if b is the square of anything, then it's in GQ. And then we also call this the quadratic residues QR. We'll never use this fact, so you can just ignore it. But these become important in other cryptographic algorithms. So when you look at things like RSA, quadratic residues are important, but they're not important here. Okay, so that's all I wanted to say about the group stuff. Is there any questions? It's a good place to pause and just make sure that there's no questions. Yeah. Yeah, so if once you've found a safe prime and you fixed it, everything of order q will have the exact same group. So there will be one group of integers for that safe prime. And then, and it's also the same as the set of integers and all that type of stuff, yeah. So if you change the safe prime to a different safe prime, it will be a different set of integers, but it will have all the same properties, and there'll only be that one group.
And is there any rule for each number, like included G?
Yeah, good question. So is there a rule? So the rule is actually this, which is the numbers are the quadratic residues. That's the rule for it, yeah? So it's the squares of everything, and that's what gets you into group Q, yeah. Now what we do in practice is sometimes again, I said that the groups have to be a multiple of Q minus 1, or they're a divisor of Q minus 1, so you multiply them. Usually what we do is we choose a really large P. So we choose a prime that's very big, and then we choose a Q that's actually a lot smaller. And we do it for efficiency reasons. But anyways, I'll make a note of that. But again, just in terms of your ability to understand Planck, you don't have to worry about any of these stuff. This is all just efficiency rules. Yeah.
If we wanted to expand or review this topic in a discrete math or what would be the header of the topic?
So this is all under number theory. But it's number theory covers more than just this, right? It's a huge thing, yeah. And so you could search safe primes in cryptography or multiplicative subgroups. That would be, yeah.
And so you will be providing this on Moodle also?
Yes, yeah. So all the notes, the video of what I'm saying is on Moodle, and yeah.
But there will be no slides or something like that, right?
So what you'll get is this exact thing that I'm writing out. Yeah, and you'll get a video recording of what I'm saying right now, yeah, and my screen.
And for more, it's going to be just for information, or it's going to be also exam stuff here?
Well, maybe like a basic exam question on this. I don't know, just to make sure that you get this stuff. But we're going to do something with it, and that's definitely the emphasis. So I don't ever want to say that like this will never be on the exam. It's like, I don't know, maybe it will be, but it's definitely not the emphasis of what we're doing. Yeah.
So there will be sample questions for the midterms?
Probably not. Yeah, I don't have the. If I had taught the class before last year, I would just give you last year's midterm, but I don't have last year's midterm. But wait till the midterm itself, and then you can ask me more detailed questions, and I'll try to. I'll give you some pointers on it. Honestly, if someone came to me and said I have to make sample questions, I'd probably just give the lecture notes to ChatGPT and have it generate, which you could do yourself, right? So you'll get the same sample questions anyways. So that's one way that you could test yourself. But, yeah. Oh, good question. I should lock that in, right? So I'm sort of indifferent. Usually I do the week before reading week or the week after. Does anyone have a preference? Would you prefer the midterm the week before reading week or the week after reading week? So after means that you have the week to study. The problem with after is usually every course puts it after, so you're probably going to have a whole bunch of things. And then the longer you wait, the more material that would be on the midterm as well. So before wouldn't conflict, and there would be one less week material that you would have to cover, but you wouldn't have reading week to prepare. After would mean that you would have the week to prepare, but there would be more material, and it would maybe conflict worse with your other classes.
Like after a week, you mentioned you want to be
Sorry,
after reading week.
yeah.
So you mentioned that you weren't gonna be there.
Yeah, for the next.
Oh yeah, sorry. Yes, I did mention that. It turned out that I was mistaken about when reading week was. Usually it's like 6 weeks, and then the second 6 weeks are. But this year reading week is after week 7, so it's the same week that I'm away.
Oh,
Yeah,
okay.
so that
So-
doesn't matter. Yeah. Okay. Who wants? We'll do a simple vote. Whoever you come to class, you have a privilege to participate, and you don't have to vote if you don't want. So option A is going to be the week before the reading week, and option B will be the week after. Okay, so let's start with the week before. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9. I think that's going to carry. The week after. 1, 2, 3, 4. Okay. So the week before. Sorry? Yeah. True. Okay. All right. So week after will be the midterm itself. I'll figure out what date that is. But sorry, the week before reading week. What did I say? Just give me a sec. Let me just figure out what day that actually is. 25. 26. Okay, so 26 midterm. I'll write it into the notes so that if I do it wrong, you can all point at this and say, no, you were March 26th.
It's February.
Yes, thank you. Now, luckily, I think it's one of those weird months where the February and March have the same dates. Let me just check that. Yeah, okay, February. So notice that Thursday, March 26th and February 26th is also the same. Why is that? Why do they have the same, why are the same things on the same days on the same numbers? Exactly. So how many days in the week are there? Okay, are the number of days in February divisible by 7?
Yes.
Okay, so if you mod by 7, then you end up with the same thing. So now you understand it. Then what happens in a leap year? So a leap year, you have 29 days in February. Is it divisible by 7 anymore? No, and so it breaks down, and so then you don't get the same property. So it happens three every 4 years. Okay, so this is the midterm. Okay, so let me just say a bit about this in practice, and then I'll turn to what we want to do, which is called the discrete log problem. So in practice,
Are you sure the reading week is that late?
I'm pretty sure. I checked it a million times for my other class, but we can check it together. That's why I was surprised. Like, that's why I thought I would be away a different week. It's because normally it isn't that delayed. But what am I looking for? Oh yeah, and then there was a question about the final, which I'll talk about too. Yeah, so March 2nd, the reading week begins. Okay, and then the final. I mentioned this in lecture 1, so if you didn't see lecture 1, watch it. But the final, I don't choose the date of. So it can be any time between April 16th and May 3rd, chosen by the department, or by the, not even the faculty, I think by the university. And I don't know when they announce it, but it won't be this month. It will be sometime mid next month, kind of, usually.
Question is, sir, are you gonna do the midterm with the final also?
Yeah, so the final will be comprehensive of the midterm. It's Concordia policy. Sometimes students miss the midterm for medical reasons or things like that. And so then they just get a final, and whatever their grade is on the final counts for the midterm as well. So I have to test them on the full material itself. Yeah. Okay. I know people want to go, but just let me write down this one thing, and then we'll save the discrete log problem for next class. Okay. So in practice, I just want to talk about what P and Q look like. So there's basically like 3 settings. So setting 1 is that you actually use a safe prime. In this case, you're probably going to use a P that's maybe 496 bits long. Okay, so that's a number between 0 and roughly 2 to the 496. This is an enormous number. Kind of think of like the number of atoms in the universe. That's sort of it. So those are all the things that P could be. And then if it's a safe prime, Okay, how long is Q going to be? Well, Q is half the size of P, right? Q is half of, right, so 2Q plus 1 is P. So we know Q is half, okay? If I have a 4096-bit number, and then I take a number that's half as big, how many bits is it? Okay, so everybody who doesn't understand exponentials, that's what I was hoping people would say. Is that actually true, though? Okay, so think about what does exponential growth look like? Okay, so think of a chessboard and there's 1 grain of sand. The next one has 2, the next one has 4, the next one has 8, the next one has 16. Okay, what's half of 16? 8. Which square, was that halfway? Do you go halfway back the checkerboard? No, 8 was just on the previous square, right? Because every time you double it, right, that's what it means. So what's the answer to the question? Okay, so it's going to be 495, right? So that's going to be half as big. So that's what exponential growth means. When you have 2 to the something and you cut it in half, you're eliminating half of it, but you only went down by 1 bit. Then you get rid of another half, and then you only go down by 1 bit. That's why these numbers are so big, right? So then we have 4095, okay? Now, in practice, we do the same thing that we did, but we don't use safe primes. We use something that's almost like a safe prime. It looks like P equals 2 alpha Q plus 1, where there's some other number here, like a scalar. And what we can do is we can make Q like really small. So what we'll do is we'll keep P at 4096, and we'll make Q like 256 bits. The reason why it's 256 we'll talk about, you'll see it later when we talk about commitments. And then there's a third setting that we use in practice called elliptic curves. Here, P is not numbers anymore, so it's going to be points on an elliptic curve, so the underlying thing will change. But Q will also be, it will be integers, just like we're used to. And it will be 256 bits as well, okay? And everything that we do in Planck will be in the exponent, and so we don't really ever care about these things, except for one operation called a bilinear pairing. Okay, are there questions about this stuff? Yes.
So in that small thing, we are using the safe prime property.
Yeah, so in this one, right? Yeah, so it's almost all this, it's actually all the facts that I told you here are the same. The only fact that's not true is number 5. So number 5 is only true in the first setting. It's not true in the bottom 2 settings. So it can be hard to find that first generator, or if you have like a message and you want to map it into an element of the group, say you're doing a digital signature and whatever reason you have to do it, that gets hard as well. In the protocol that we're doing, we never have to do that. So first off, okay, I tell you P is 4096 bits, that's fine. How do you actually choose that P for yourself? The answer is you're probably not going to choose it for yourself. There's an organization in the United States called NIST, and they've already chosen these for you. Okay, so you can just use the NIST-defined P and Q, and then they'll also give you a G. So here it's easy to find a G anyway because you can square it, but here it's a bit of work to find a G. You basically have to do kind of like a brute force for it, and so what they'll do is they'll say, here's a P, here's a Q, and here's a G, and then you can just go ahead and use that one. Yeah, and then for elliptic curves, they'll say, here's the curve that you're using, here's the generator, and it will have order Q. Okay, so in practice, all this stuff will be given to you by NIST, and then in software, it's going to be given to you because the software developers implement it using some parameters that were given to them by NIST or whatever. And it's not necessarily NIST, it's just an example, but it's the one that standardizes a lot of stuff. Okay, questions? Okay, great. I'll see you all next week.